All right, in this video, we're going to take a look at solving rational inequalities. We're going to break this objective up into two separate videos just for time purposes. But when solving rational inequalities, our critical values that we're going to set up our number line with are going to be wherever the denominator equals 0. And if we treat the inequality as an equation, the solution to the inequality treated as an equation. So we'll see some examples of that in this video and the next. So regardless of anything else, the critical values of the denominator, because we don't want the denominator to ever actually equal 0, on our number line, those critical values are always going to be open circles. So no ifs, ands, or buts. The values that cause the denominator equals 0 are always open circles on our number line. So example 2, solve each. Write your answers using interval notations. We have 3x plus 9 over 2x minus 5 is less than or equal to 0. We can start by finding where the denominator would equal 0, so we want to avoid those. So we're essentially finding the domain of this rational function at the start. So 2x minus 5 equals 0 means x is 5 halves, so we definitely do not want x to equal 5 halves because that would cause our denominator to equal 0. So it's going to be an open circle for that value on the number line. Now for the numerator, 3x plus 9, and then we still have it over 2x minus 5. If we set 3x plus 9 over 2x minus 5 equal to 0, we can clear out our fractions by multiplying both sides by 2x minus 5. And if we multiply 0 times 2x minus 5, we get 0. So our numerator, 3x plus 9, would just equal 0. And that's one of the benefits of having 0 on the right-hand side, is you can just set your numerator and denominator both equal to 0 and solve. But that only applies if you're starting with a 0 on the right-hand side. Or you could do it if you find an expression, rewrite the expression for that. So 3x plus 9 equals 0 means x equals negative 3. And then we can set up our number line with negative 3 and positive 5 halves. The negative 3 can actually equal, because if we plug negative 3 into the original function, we get 0 divided by negative 11, which is equal to 0, and 0 is less than or equal to 0. So we have a closed circle at negative 3. As we said earlier, the 5 halves would cause the denominator to equal 0, so that automatically at 5 halves is going to be an open circle. And now, just like with polynomial inequalities, we can use test values. We can test out a number in the original problem that's less than negative 3. We can test out a number in the original problem that's between negative 3 and positive 5 halves. And then we can test out a number in the original problem that is greater than 5 halves. When we do that, we find that the only numbers that'll work are the values between negative 3 and positive 5 halves. So for instance, x equals 1 would work because that will result in the left side being less than or equal to 0. So our final answer is between negative 3 and positive 5 halves, where we include the negative 3, so a bracket before negative 3, but we do not include the 5 halves, so a parentheses after the 5 halves. All right, example 2, part B, we have 4 minus x over x plus 1 is greater than 2. So this one is not equal to 0 at the start, or not greater than, or whatever, does not have a 0 on the right-hand side. So we cannot use that shortcut of setting the numerator and denominator both equal to 0. So we'll start with the denominator, x plus 1, not allowed to equal 0. So let's find the value of x that would cause that. Well, it'd be x is negative 1. So on our number line, we're going to have an open circle at negative 1 for x. Now, for the second part, we're going to treat this like an equation. So 4 minus x over x plus 1 equals 2, or 4 minus x over x plus 1 equals 2 over 1. And then you can multiply both sides by x plus 1 to clear out your fractions. Sometimes people refer to this as cross multiplication. So in any event, you're going to get 2 times the expression x plus 1 equals 4 minus x. So I guess you could cross multiply here. 2 times x plus 1, when we distribute that 2, we get 2x plus 2 equals 4 minus x. And then if we add x to both sides and subtract the 2 from both sides, we'll get 3x equals 2, which makes x equal to 2/3. So our number line values are going to be negative 1 and positive 2/3. So if we test out some values on our number line here, well, before we do that, let's look at the negative 1 and 2/3. We know that negative 1 has to be an open circle because it causes the denominator to equal 0. If we plug in 2/3 in for our expression, we actually get 2 greater than 2, which is not a true statement. So because plugging in 2/3 for x does not give us a true statement, we have to use an open circle for that. Now we can test out a value less than -1 between -1 and positive 2/3, and a value also greater than 2/3 in this original inequality and see if it makes it true. And only values between -1 and positive 2/3 will make our original inequality true. So in interval notation, we have parentheses around the expressions -1 and positive 2/3. Looking at a visual interpretation of this, our original problem was 4 minus x over x plus 1 greater than 2. So in blue, we have the graph of 4 minus x, the graph of that rational function. In purple is the graph of y equals 2. And what the original problem is asking us is, where is the graph on the left above the graph on the right? So it's above the graph on the right-hand side when our values of x are between -1 and positive 2/3. So here, this piece of the graph in blue is the only part of our graph that is above the line y equals 2. All right, so that about does it for this video. We'll do some more examples in the next one, so I'll see you then.